để review recursion và counting. Câu thứ nhất, trong một cái phi trường có nhiều cái locker, mỗi cái locker nó được đánh dấu với một cái uppercase và theo sau là 3 cái chữ cái. How many different label 26, cái này 3 chữ cái là 10, vậy là 26.000. Dùng quy tắc nhân ở đây. How many element trong cái đề khác product của một cái tập k phần tử và một cái tập l phần tử. Câu C, dùng quy tắc tích, đúng rồi. Cái tích đề khác này là giống như quy tắc tích vậy. Ví dụ các bạn có 3 phần tử A, B, C. Bên này các bạn có phần tử là 1, 2. A này các bạn chọn 1, cộng A đó các bạn chọn 2 này. Thì các bạn thấy là mỗi phương án của bên này thì nó ứng với bên này là 2 phần tử. Bên này nếu các bạn lấy B thì cái điều tương tự cũng xảy ra, B1 và B2. Thì các bạn cũng có 2 nữa, đúng không nhỉ? Thì là các bạn 2 nhân 2 nhân 2. Còn nếu bên này là K lần, còn bên này là L là nhân cho K. Theo quy tắc, how many 8 discrete? Start with 1 or end with 0, 0. So we have here the set of starting with 1. The rest is 7 bits. So here we can choose 0, 1. Here we can choose 0, 1. And etc. Here we choose 0, 1. And the sum of here is 2 power of 7. Now we consider the A bit string end with 0, 0. 1 bit string here and 0, 0. So the rest is 6 bit. In the same way, we have a 2 power of 6. Because one element in the intersection, if we count the element in the A, and then we also count the element in the B. So the element occurs 2 times in the counting. Did you remember the subtraction rule? We have here the cardinality of A plus the cardinality of B, and then we minus the cardinality of 2 power of 7, and here 2 power of 6. So now we need to determine the cardinality of the intersection. For the intersection, because one element in the intersection starts with 1 and end with 2, 0. So we have here 5 bits. We have 2 power of 5 bit string. So here we have to minus 2 power of 5. Let's use a calculator and we show me the correct answer. I use a calculator in the window. 2 power of 7. 2 power of 7. 2 power of 6. We have 64. 2 power of 5. 32. We have it here. The correct answer is D. For the next, the cardinality of the set S is 8. Here, we need to specify the condition. The condition here is contain 3, but not contain 5. We always choose 3. Say not contain 5, so we delete the 5. Now we choose here. How many ways to choose from the subset here? 6 elements. 2 power of 6. Yes, the correct answer is 64. The next here, we have a recursion. The initial term f0 is 1, f1 is 4. This is the recursion formula. So we have f2 is f1 multiply f0 and then plus 1. Because here f1 is 4, f0 is 1. So we have it here, f2 is 5. Because f2 is 5, we should choose here. Try to check f3, f2 multiply f1 plus 1. So 21. The question 7. What is the purpose of the procedure? So here we can write and n is 0. The reason here the base case is what? And for the n is greater than or equal to 1, fn is 2 fn minus 1. We use here the loop technique, fn to fn minus 1, because fn minus 1 to fn minus 2. So we have it here 2 power of 2 fn minus 2. So here fn minus 2 equal to 2 fn minus 3. So here we have 2 power of 3 fn minus 3. And so on. We have to try to the base case. Because the base case n is 0, so we have here 0. What is here? So here we have 2 power of 1, and we have here 1. Here 2 power of 2, and here n minus 2. Here minus 3, so we have here 2 power of 3. So here f0 it means fn minus n. So here we have 2 power of n. Because here we have f0 is 1. So multiply 1. So 2 power of n. The correct answer is C. This is the loop technique. The technique is more commonly used to solve recurrent relation. It means we want to find the explicit formula. From the explicit formula, we can know the purpose of the procedure here. This is the return Pascal language. This is the exciting question that I see. 10 options for one digit. Let us consider the condition. The condition here, both begin and end with 99. Have it here. Begin with 9 and 9 and end with 9 and 9. So the rest is just 6 digits. We have 10 power of 6. The correct answer here is we have 10 digits. 1 plus 2 plus 3 and then n is n plus 1 2. We can prove the statement here by using mathematical induction. Suppose that the sum of 1 to k is k multiply k minus 1 2. To prove p of n is true, we need to use the hypothesis here to prove p of k plus 1 is also true. So it means we have to prove the sum here is k1 k plus 1 and plus 1 divide 2. We add the left side here k plus 1. We have 2 plus here k plus 1. So here we have k multiply k plus 1 and plus 2 times k plus 1. Here is 2. So now we get the k of 1 as the common factor. Here the rest is k. The rest here is 2. And here is 2. We have just proven that. So A is the correct answer. Now we want to prove the second. The second here is a geometric progression. We did not P of n here. We want to prove P of n is true. In the first step, let P of k is true. So we have 2, 0, 1, 2 power of k, a 2 power of k plus 1 minus 1. We have to prove P of k plus 1 is true. So we want to prove here using the hypothesis. From here, in the left side, we have 2 power of k plus 1 minus 1. and then plus 2 power of k1. We have a 2k plus 1 minus 1. So we have here, we have just proven the fact B. To prove C by using mathematical induction. We denote here P of n is a statement and G n is divisible by 3. N is greater than 0. So the base case is P of 1. 1 power of 3 minus 1 is divisible by 3. Equal to 0 is divisible by 3. This is true. Let k power of 3 k is divisible by 3. So we want to prove k plus 1 power of 3 minus k plus 1. K 3k square, 3 of k plus 1, and then minus k minus 1. So here k 3 plus 3k square plus 2k. So here k3 minus k, 3k square, 3 times of k. And here k3 minus k, we can get 3 as the common factor. So here k square plus k. Because we have here, this is 3 times of any integer is divisible by 3. We can conclude that C is true. This is the correct answer. For the next question, a coin is tossed 3 times. How many possible outcomes are there? So in the first, so we have a head or a tail. We use here the product rule. So the correct answer here is A. For the next, we can write here n factor is n multiply n minus 1 factor for n is greater than or equal to 1. And we have 1. This is the correct answer. And here it means the case n is 0. Tab, we have an explicit formula. From the explicit formula, we can find the recursion definition. The first term, f0 is 5, f1 5 multiply 3, f2 5 multiply 3 square. You can see here, from the previous term here, we multiply with 3. From the previous term here, from the previous term here. So we have fn is fn minus 1 multiply with 3. The base case is 5. For n is 0. The recursion case for n is greater than 0. The correct answer here is A. We start from the 0. 0. Here may be true, but it's not good. Because here we start from 1. So the definition does not describe the case n is 0. We have here the recurrent relation. An is an minus 1 plus 2 times of n. And is 0, 2. We want to solve the recurrent relation here. You must find the explicit formula. Did you remember the loop technique? We do a recurrent progress. We can replace here with an minus 2 plus 2 times of n minus 1. Here. And the rest is 2 times of n. Focus here. We have an minus 3 and then 2 times of n minus 2. The rest here 2n minus 1 and 2 times of n. We should think about the rule in the progress. You can see here 3, here 2, and 2 minus 1. Here I think minus 0. We have it here 2 minus 0, and here. If we apply the same rule to make the base case, we should write here a n minus n. means a 0. Because here we have an n, so the rest is 2 times of n plus 1 and n, and then 0. Because it is 0, an 2, so I think an 2 times of the summation from 0 to n plus 1. So here we have n plus 1, n plus 2, divide 2. We can reduce 2. We have n plus 1 multiply n plus 2. And here the correct answer is A. Question 14. Suppose that Fn satisfies the divide and conquer relation. What is F81? F81 is 2 times of F81 divided 3. It means F27 plus 5. 2 times of F27 divided 3 plus 5. So here we have 2 power of 2 F9 plus 2 times of 5. Try to continue. F9 2 times of F3 plus 5, and the rest is 2 times of 5. F3 plus 2 times of 2 plus 2 multiply 5. Inside 2 times of F1 plus 5, and the rest is plus 2 times of 1 multiply 5. Here F1 plus 2 times of 2, 2 times of 1, and multiply with 5. I missed the 5 here. Plus here 2 power of 0. I'm sorry, 2 0, and plus 2 power of 0. F1 is the base case. Multiply 5. Did you remember the second? This is the geometric progression. 2 power of 4 minus 1. So here, and the rest. So we can write here. One is 5. Here is the correct answer. Here, the procedure is writing in Pascal language. We can write to Fn is n plus Fn minus 1. N is greater than 1. So if n is 1, the base case, we have 1. And 15 plus F14. Try to F1. If here is 1, what's E here? 2 here. Because in 13, 14, here 14, 15. So in the stop case, 1. So here we have a 2. We have the sum from 1 to 15. Yeah, this is the correct answer. How many one-to-one functions are there from the set of A, B, and C to the set of X, Y, Z divided K? 1-to-1 means if we choose H for A, we cannot choose H for B. So for A we have 6 ways. So for B we have 5 ways. For C we have 4 ways. Here, with the following a recursive definition of the set. To describe the set, we can use a recursion. So 1 belongs to S. If we have n belong to S, 2 belong to S. 1 is in S. If it is in S, good. No, because here yes. Question 18. How many 4-bit string not have 2 consecutive 1 bit? We want to find the formula in the general. If we let Fn, the number of 4-bit string do not have 2 consecutive 1 bit. If we know Fn minus 1, you can use tree diagram, but just for we can use the complement rule here. Find the 4-bit string to consecutive one. And let's try to find the recurrent relation. You can post for. You can use the tree diagram. You can use the complement rule. You can use somewhere. But if here we have a large number, I think impossible. And n is 1, we can choose 0 or 1. So if n is 1, we have at 1 is 2. And at 2, we have 3 options, 0, 0, 0, 1, 1, 0. So at 2 is 3. If we have the current relation at n is 2, if n is 1. So we can use the description here to compute F4. This is advanced counting techniques. F4 is F3 plus F2. F3 is F2 plus F1. So, and we have 2 F2. F2 is 3 and F1. F1 we have 2. The reason here is 8. In here we have applied the advanced counting. I can write here the explicit formula, but we have no time. Ở đây mình có thể giải ra được cái công thức tường mình luôn. Người ta muốn các bạn đếm độ dài 9 tỷ chẳng hạn, tức là các bạn đi tính cái f của 9 tỷ. Các bạn thế vào công thức đó thì nó sẽ ra là bằng bao nhiêu luôn. We can